For every bond, the wave number of absorption associated with the bond stretching is dependent on two factors: the bond strength and the masses of the atoms sharing that bond. The impact of these two factors can be rationalized when we treat a bond as if it were a vibrating spring connecting two weights. Using this analogy, we can construct the following equation derived from Hooke's law, which enables us to approximate the frequency of vibration for a bond between two atoms of mass m1 and m2. In this equation, F is the force constant of the spring, which represents the bond strength of the bond, and m reduced is the reduced mass of the system. Use of the reduced mass in this equation allows us to treat the two atoms as one system. Notice that the reduced mass appears in the denominator. This means that smaller atoms give bonds that vibrate at higher frequencies, thereby corresponding to a higher wave number of absorption. Also notice that the force constant is in the numerator. Therefore, the stronger the bond, the higher the stretching frequency will be. You don't have to memorize this entire equation. It's just a good idea to know that wave number is directly proportional to the force constant, or the bond strength, and it's inversely proportional to the reduced mass, which is equal to the product of the masses of the atoms divided by the sum of the masses of the atoms in the bond. The trends in stretching frequency of given bonds can be rationalized based on the bond strength and mass difference. We see some examples here. In number 1, we have a bunch of bonds to carbon. So we have a carbon-hydrogen bond, a carbon-deuterium bond, a carbon-oxygen bond, and a carbon-chlorine bond. And what we see is that as the mass of the atoms that are bound to the carbon get heavier and heavier, you see that the wave number decreases. Why would that be? It would be because the reduced mass increases, and the reduced mass is in the denominator. If you just do a quick calculation for the reduced mass, so if you do a quick calculation for the reduced mass of a carbon-hydrogen bond, so it would be 12 times 1 divided by 12 plus 1, so that would be 12 over 13, which gives you around 0.92, something like that. If you were to do it for the carbon-oxygen bond, then you have 12 times 16, which gives you, so the reduced mass would be 192 divided by 12 plus 16, which is 28. And so that would give you around 6.9. And so you can see, again, that as the mass of the atoms increase, the reduced mass increases. Again, the reduced mass is found in the denominator, and so the wave number will decrease as the mass of the atoms in the bond increases. If we look at number 2, you can see that these are all bonds between carbon and nitrogen, but we go from a triple to a double to a single bond. What we know is that if we go from a triple to a double to a single bond, the bond weakens. It gets less and less strong. So the strength increase is going in this direction. And since bond strength, which is the force constant, is in the numerator, the stronger the bond, the higher the wave number of the absorption will be. The weaker the bond, the lower the wave number of the absorption band will be. Again, you don't have to memorize this entire equation. What you need to know is that the wave number is directly proportional to the force constant, and it's inversely proportional to the reduced mass, and you should know what reduced mass is and how to calculate it. Using these two trends, we can understand why different types of bonds will appear in different regions of an infrared spectrum. And we see different bonds in different areas of our infrared spectrum here in this figure. Single bonds, except for anything that's bound to hydrogen, appear on the right side of the spectrum, down here, because single bonds are generally the weakest bonds. Double bonds appear at a higher wave number because they're stronger than single bonds, while triple bonds appear at an even higher wave number because they're even stronger than double bonds. And finally, on the left side of the spectrum, we see the signals produced by bonds to hydrogen, such as a carbon-hydrogen, an oxygen-hydrogen, or a nitrogen-hydrogen bond, all of which stretch at a higher wave number because hydrogen has the smallest mass. Infrared spectra can be divided into two main regions. The diagnostic region, which is greater than 1,500 reciprocal centimeters, generally has fewer peaks and provides the clearest information. This region contains all signals that arise from double bonds, triple bonds, and anything bound to hydrogen bonds. The fingerprint region, which is less than 1,500 reciprocal centimeters, contains signals resulting from the vibrational excitation of most single bonds. This region generally contains many signals and is more difficult to analyze. This region is called the fingerprint region because each compound has a unique pattern of signals in this region, much the way each person has a unique fingerprint. To illustrate this point, compare the spectra for 2-butanol and 2-propanol. The diagnostic region of these compounds is virtually indistinguishable, so that is above 1,500 reciprocal centimeters. They're virtually identical. But the fingerprint region of these compounds are very different. Now, if we go back a couple of slides, we said that a carbon-hydrogen absorption occurs around 3,000 centimeters to the -1 or reciprocal centimeters. But let's look at this in more detail, and let's look at it with respect to the hybridization of the carbon, because we can have a carbon-hydrogen bond where the carbon is sp3 hybridized, we can have a carbon-hydrogen bond where the carbon is sp2 hybridized, and we can have a carbon-hydrogen bond where the carbon is sp hybridized. And so we can differentiate between these three types of carbon-hydrogen bonds based on the hybridization of the carbon. Why can we do that? Well, as we go from sp3 to sp2 to sp, what do we see? We see that the S character of the carbon increases, right? An sp3 hybridized carbon is 25% S, 75% P. An sp2 hybridized carbon is 33% S, 66% P, and then when we get to sp, it's 50-50, right? It's 50% S and it's 50% P. But we know that an S orbital is smaller than a P orbital. And so the bottom line is that the shorter the bond length is, and we discussed these kinds of bond lengths earlier in the class, but we know that the bond length decreases as we go from sp3 to sp2. And what happens as the bonds get shorter, they also get stronger. And so the sp hybridized carbon-hydrogen bond would be the strongest bond, and the sp3 hybridized carbon-hydrogen bond would be the weakest bond. And we saw earlier in this video how bond strength is associated with wave number, with absorbance. The stronger the carbon-hydrogen bond, the higher the stretching frequency of the carbon-hydrogen bond. And so we can look at an infrared spectrum and we can differentiate between an sp3 carbon-hydrogen bond, an sp2 carbon-hydrogen bond, and an sp hybridized carbon-hydrogen bond. If you compare the spectra of an alkane, an alkene, and an alkyne, in this figure that I have shown here, in each case we have a line drawn at 3,000 reciprocal centimeters, and that's the line that's in red, so we have it here, here, and here for each of these. All three spectra have signals to the right of the line resulting from the sp3 hybridized carbon-hydrogen bonds. So that's these ones here, and these ones here, right? We have an sp3 hybridized carbon-hydrogen bond. The key is to look for signals to the left of the line. An alkane doesn't have any signals to the left of 3,000 reciprocal centimeters. An alkene has a signal at around 3,100 reciprocal centimeters, and an alkyne has a signal at around 3,300 reciprocal centimeters. And so the take-home message from this slide is that you can differentiate between carbon-hydrogen bonds and the carbon hybridization. If we only have signals to the right of the line, we know that it's a sp3 hybridized carbon-hydrogen bond. If we have a signal at 3,100, it's sp2 hybridized. And if we have a signal at 3,300, it's going to be sp hybridized. But be careful, the absence of a signal to the left of 3,000 centimeters to the -1 does not necessarily indicate the absence of a double bond or a triple bond in a compound. Tetrasubstituted double bonds do not possess any sp2 hybridized carbon-hydrogen bonds. And internal triple bonds also do not possess any sp hybridized carbon-hydrogen bonds. Let's consider the effect of resonance on the wave number of absorption. As an illustration, let's compare carbonyl groups in these two compounds right here. The second compound is called an unsaturated conjugated ketone. It's unsaturated because of the presence of the carbon-oxygen bond, and it is conjugated because of the pi bond that's separated by exactly one sigma bond. So we have a pi bond, then we have a sigma, then we have another pi here. So when pi and sigma bonds alternate like that, we call that a conjugated system. Now, as you can see, the carbonyl group of the unsaturated conjugated ketone produces a signal at a lower wave number. So it's at 1680 centimeters to the minus 1, whereas the carbonyl group of the saturated ketone comes out at 1720. In order for us to understand why this is, we must look at the resonance structures for each compound. Ketones have two significant resonance structures. The carbonyl group is drawn as the double bond in the first resonance structure, and it is drawn as a single bond shown here in the second resonance structure. This means that the carbonyl group has some double bond character and some single bond character. In order to determine the nature of this bond, we must consider the combination from each. In order to determine the nature of this bond, we must consider the contribution from each resonance structure. In other words, does the carbonyl group have more double bond character or more single bond character? The second resonance structure exhibits charge separation as well as a carbocation that has less than an octet of electrons. For both of these reasons, the second resonance structure contributes only a small amount of character to the overall resonance hybrid. Therefore, the carbonyl group of the ketone has mostly the double bond character. Now, if we look at the unsaturated ketone, it has 3 resonance structures rather than 2. In the third resonance structure on the bottom right, the carbonyl group is drawn as a single bond. Once again, this resonance structure exhibits charge separation as well as a carbocation with less than an octet of electrons. As a result, this resonance structure also contributes only a small amount of character to the overall resonance hybrid. Nevertheless, this third resonance structure does contribute some character to the overall resonance hybrid, giving this carbonyl group slightly more single bond character than the carbonyl group of the saturated ketone. With more single bond character, it is a slightly weaker bond and therefore produces a signal at a lower wave number, 1680 instead of 1720. Esters exhibit a similar trend. An ester typically produces a signal around 1740, but conjugated or unsaturated esters produce lower energy signals, usually around 1710. Once again, the carbonyl group of a conjugated unsaturated ester is a weaker bond due to resonance. And so the bottom line, or the take-home message for students in this class, is that when you have a conjugated ketone or a conjugated ester, the absorbance of the carbonyl is going to occur at a lower wave number than it would in a fully saturated system. The absorption is going to occur at a lower wave number than it would in the non-conjugated system, like a regular ketone or just an ester that doesn't have the conjugation in it. And of course, we can relate this directly to our equation for wave number. The wave number is directly proportional to the force constant or the strength of a bond. And so when we have a weaker carbon-oxygen double bond, we're going to have a lower wave number.